Great. Well, that was a great lead-in. Whoops. Mike talked on a number of issues that I'm going to follow up on and talk about it in a slightly different way. I'm going to talk about the big picture. I'm going to talk about fossil fuels in general, what they have done historically for the planet, how much is left, how technology and economics and policy have changed our view of fossil fuels, and then look towards the future with a particular focus on the connection between energy and carbon. And while there's many things we can't imagine about the gas revolution, one thing we can very much imagine, that is if we burn all the gas that's in the Earth's crust, the Earth is going to be a very much warmer place. And when you add all the coal and oil on top of that, we're looking at a world that is radically different than the world today. We do have our biases. I'm not pro-fossil fuels and I'm not anti-fossil fuels. But I do know that the consequence of burning fossil fuels has enormous implications for future generations. And I think that has to be front and center in our discussion about what we do with these resources. So, a bit of backdrop. Those of you who have been involved in this course, I'm sure have seen this information before. Excuse me. This is probably the most famous data set in the environmental science world, which is the Mauna Loa curve, which shows along the vertical axis the concentration of carbon dioxide in the atmosphere. Of course, CO2 is the principal greenhouse gas. You see this increase in greenhouse gas concentrations over the past few decades. We know that before we started burning fossil fuels, the concentration was at about 280 parts per million. We're now at close to 400. And this rise in greenhouse gas concentrations is the biggest component of the human contribution to the observed warming of the planet that we see or have observed. Those concentrations have been driven largely by the combustion of fossil fuels, also land use changes and a few other things, but largely fossil fuels. Oil and gas and coal are made out of carbon, and the energy is released when you oxidize the fuels, when you burn them, and out comes carbon dioxide. So almost and we've optimized our use of fossil fuels to completely oxidize the fuel, so that almost all the carbon that's in the actual oil, gas, or coal goes up into the atmosphere. And this shows the historical record of the release of carbon into the atmosphere. So the vertical axis is petagrams, which is 10 to the 15th grams, which is how earth scientists measure carbon. Since we started burning fossil fuels back in the late 18th century, we released about 346 petagrams. If you think in terms of tons, that's 346 billion metric tons of carbon have been released to the atmosphere. And if you want to get to actual emissions of carbon dioxide, you can multiply that by about 3.7. So you can see the biggest constituents overwhelmingly are fossil fuels, natural gas, coal, and oil. So we've seen this huge increase in the release of carbon into the atmosphere. So one of the principal questions in terms of the connection to climate is, what does the future hold in terms of availability of fossil fuel? How will emissions change in the future? Which is a function of the type of energy we use and a lot of other social and economic and technological factors. I'm going to focus on the energy part of that. So I'm going to show you some numbers. So a couple numbers to, oh good, wow, real chalkboards. Nobody gets to write on real chalkboards much anymore. They're all whiteboards and all their fancy boards. So 514 exajoules. So an exajoule is 10 to the 18th joules. One of the bane of my existence in teaching the energy world is all the freaking units that different people use to measure energy here and across the world. Joules, BTUs, kilowatt hours. Anyways, joules is the metric system way of measuring energy, which is used internationally. The world last year used 514 exajoules of energy. Totally, out of all the oil, all the coal, all the nuclear fuels, all the biomass, all the solar, 514 exajoules. And we generated about 22,000 terawatt hours of electricity, which is roughly equivalent to 79 exajoules. So that gives you a little bit of frame of reference as I throw some of these numbers around. So, how much oil and gas and coal are left in the Earth's crust? You might think that's a pretty simple answer, but it's actually quite a complex answer due to the vastness of the Earth and the complexity geologically and chemically with which some of these resources occur. So what I've shown you here is my compilation of some of the latest work that's been done on assessing how much oil and gas and coal remain in the Earth's crust. And the numbers that you're seeing here are what are called technically recoverable resources. So these are resources that have been identified and are believed to be extractable with current or near-term technology. Right? They might not necessarily be able to be extracted today in their current prices, but technologically, we think we can get our hands on them. So let's start with oil. So we have different categories of oil. And what I've shown here is recoverable potential, measured both in billions of barrels, which is BB, how much we currently produce, and then in the last column, the ratio of the recoverable potential to production. So if we look at that first row, for example, last year we produced about 32 billion barrels of oil in the world, which is about 194 exajoules. The recoverable potential, which is the amount of oil that sits in proved reserves, and the amount which we geologists believe we can extract in the near term, is about 2,700 billion barrels. So if you divide those two, you get 85, which is roughly, if you do the units, it's about 85 years worth of oil at the current rates of use. Then we move down into what are called the unconventional oil categories. Natural bitumen, otherwise known as oil sands. So these are the vast deposits up in Canada. Right? There's a whole Keystone Pipeline controversy. So they want to bring that oil from Alberta down to refineries in the Midwest and Texas. Natural bitumen, about 661 billion barrels. Very little being produced right now. So quite a long projected lifetime, although Canada is rapidly ramping that up. Move to heavy oil, which is large deposits of this in Venezuela. So this is very high density, low viscosity oil that needs usually some extra coaxing to get out of the ground. You can see the numbers there. And then we get down to oil shale, which is sedimentary rock shale that is impregnated with something called kerogen, which is an organic material. And you can literally extract the rock, crush it, grind it, heat it up, and out comes crude oil. So in the case of oil shale, heavy oil, and oil sands, you can pull out of it with some processing crude oil from which you can produce all the normal refined petroleum products, motor gasoline and jet fuel. And there's a huge amount of oil shale, which currently is not economically viable to extract, but look at those numbers. So then if we come all the way down to the bottom, and all the total liquids, which we believe are technically recoverable at this point, yeah, there's a lot of oil left in the earth. So this whole notion about peak oil, which you've probably heard about, that largely deals with the conventional category, and even there, there's probably some fairly significant amounts of conventional oil left. So there's a significant amount of liquid fuel left in the Earth's crust. Let's turn to gas. We have conventional gas, again showing recoverable potential, production. This is for the world, and the ratio. And then you move to shale gas and these other categories of unconventional gas. We just heard about shale gas and the numbers there. Shale gas is available in quantities that are almost as large as remaining conventional natural gas deposits. TCF are trillions of cubic feet. Tight gas, which refers to gas in sandstone formations where the permeability is very low, requires some extra coaxing to get out. coal bed methane. Coal actually contains a large amount of methane, which is tightly bound in what are called cleats, the small pore spaces in coal. And so you can actually drill into coal and pull the water out of the coal, and after you de-water the coal, the methane will actually flow out. And they're doing this right now in Montana and Wyoming and other parts of the world. And then there's this large category of methane hydrates. Methane hydrates are methane molecule trapped in what's called a clathrate, which is a molecular ring that exists in permafrost and shallow ocean sediments. And it traps the natural gas in there, and you can drill into it and extract it, and out comes methane. We don't know how to do it commercially yet, but there are some early tests being done now in Japan and Russia to actually look at it. And there's a huge amount of natural gas in methane. So again, if you do the numbers at the bottom, total gas, the amount of gas relative that's recoverable relative to what we currently use is enormous. 700 years worth at current rates of natural gas use. Then we turn to coal. Hard coal, so-called bituminous coal, and lignite. You can see the numbers there, and you can see at the bottom the amount of coal. GT is in gigatons. Those are metric tons relative to what's available. Notice the order of magnitude difference. So gigatons and metric tons. So there's 3 orders of magnitude difference there. And so if you do the ratio of how much is available relative to the rate at which we use, we got coal that will last for a very, very long time. Very, very long time. So, okay. What does this mean for climate? So here's a summary, I should say. So at the bottom, if we take the total recoverable potential of all the energy that I've shown you, compared to what we currently produce, 506 exajoules, and it's 1,200 times what we currently use. So there's a lot of fossil fuel left in the Earth's crust. All right, so let's get back to the climate issue now. Now let's measure the carbon that's in all this stuff. And so if we take those recoverable quantities of those various fuels and measure the amount of carbon in them in petagrams, and you can see the distribution. The total amount is over almost 15,000 petagrams, most of which is in coal. But also a fair amount in gas and oil. And so remember that, and there's a breakdown between the fuels. Remember that what we've produced thus far is 346. Okay? Do we have your attention? For those of you who perhaps aren't concerned about climate change, or believe that we only need some fine-tuning of our energy systems to deal with climate change. If we put anywhere close to that amount of carbon in the atmosphere, it'll be Venus. We'll fundamentally alter the planet's climate system in ways that make this 1 or 2 degrees C thing that we've seen in the last century be noise, lost in the signal. So a staggering amount of carbon. And so the question is, so this is a preeminent question we face as a species in some very fundamental way. And so the skids are greased to pull this stuff out, are they not? We just heard about natural gas, right? The skids are greased. 15 of the 20 largest companies in the world sell carbon. We have the infrastructure in place to burn it, and so tell me a story by which we're not going to burn it. So the way I see it, if you really want to do something, you got to get radical. Talk about what was the term that you used? The term for natural gas, and disruptive. Talk about disruptive. If you're really concerned about climate, then the changes you make it'll be a level of disruption and make the shale gas revolution seem pretty tame. And so if you believe that something has to change to prevent this carbon from entering the atmosphere, what has to happen? Well, you got to start using non-carbon fuels. And so here's some assessments that I've gathered. Most of this comes out of the IPCC assessment of renewable energy. Sorry to make you work so much, follow me around.
I'm on the chart
now. The IPCC assessment of renewable energy and some of the other recent work. So here's renewable energies, their technical potential. Again, what we believe we can produce from renewable sources with current and foreseeable technology, what we currently produce. And the last column, the technical potential relative to that 22,000 terawatts we currently generate. So solar energy, so now we're looking at flows, right? Not stocks of carbon, this is flows of energy per year. Big variations in the estimates based on different assumptions about just how much of the land can you cover with collectors, how much do we want to save for parks and geese and parking lots and Walmarts and universities and other things, what the efficiency of solar collectors are and various other things. So there's a huge range in estimates. But even in that range, look at the small amount we produce, that second column, relative to what's available. So a large possibility for expansion, and solar electricity, photovoltaics, and to a lesser extent solar thermals could supply a very large resource. Hydropower, we can see the numbers there. That's the most well-developed renewable energy source. 53 exajoules per year potential. We already produce about a quarter of that, but it still has a significant amount of untapped potential. Wind, you can see the numbers there. Large variation there. Again, assuming where you can put wind turbines, and there's all kinds of discussions about the performance of wind turbines. Biomass, lots of issues there, because then you start talking about food and fuels, the right to use corn to power your SUV when people are starving, all these issues. A lot of issues related to land use. You have to know a lot about global commodities markets when you start talking about diverting soybean and corn to fuel production. So a lot of range of uncertainty there. There are even some people in the biomass who believe the potential is zero because we're already fully committed and we can't divert any land away from food production to fuel. Geothermal energy, you can see there, and ocean energy. And so if you look at that, the middle column, you can see, with the exception of hydropower and biomass, how little renewable energy currently is actually produced. Right? Remember, 514 exajoules, yeah, it doesn't add up to a lot. And half of that biomass is traditional biomass in developing nations. So fuel wood and animal dung, which are burned to heat and cook with. So modern renewables, take out hydro for a minute, which has been around for a long time, but modern renewables, solar and wind, are a little itsy-bitsy fraction of total energy use right now. They're one of the fastest growing energy sources in the world, but in terms of the absolute contribution to our energy budget, minuscule.
Could you explain your last column, the multiple?
Yes, so if you take I'm sorry for not explaining that. So you take the technical potential of that much energy use and divide it by total electricity use. So solar energy could supply 20 to 300 times all the electricity we currently generate in the world. That's what that number means. So solar electricity, if you take those numbers, could supply 20 to 30 times that number. So if you look at the renewables, solar is where it's at in the long run. I mean, wind is great, and wind is making the earliest penetration of renewables, but it has a very limited capacity, a large capacity still, but much smaller than solar. So solar is where I put my money in the long run. And it also has great potential for technological improvements with solar cells. Okay, so is disruptive rapid change possible? Well, it has happened in the past in major ways that have fundamentally altered the trajectory of civilization, which is what we're talking about here. if you want to get serious about climate change. So you're talking about fundamentally altering the trajectory of civilization. And it has happened. Some foundations and governments and the World Health Organization got together and eradicated smallpox. It's amazing. It's amazing. The Green Revolution, the Ford and Rockefeller Foundations, the government of the Philippines and Mexico and a few other people got together, and within a couple of decades, quadrupled the yield of basic grains. India went from losing 5 million people in a famine when the monsoons failed to being a grain exporter. The Manhattan Project, right? Get out the checkbook, get the best scientists, major scientific and engineering advances in a very short window of time. So how these actually happened, of course, there's very different stories behind them, but I guess my point is that we need, if you want to be serious about climate change, then you need something like this that is transformative and fairly rapid. And so what are the barriers to that? Well, one are the enormous sunk costs in the fossil fuel infrastructure, which create inertia. And these sunk costs are growing, right? You talk about LNG, I guess, I don't know, Qatar is not too happy about the low gas prices, but Qatar, Indonesia, and Australia, massive investments in liquefying natural gas to export it to China, Japan, and European markets. The pipeline infrastructure in the United States, the Keystone Pipeline here, Russia is building lots of big, expensive gas pipelines, coal export terminals in Australia, you name it. So we have these huge investments which last a really long time. So that leads directly to the next point, is that major energy transitions historically have taken a really long time. And this shows the energy transition in the United States since about 1780. Some work done by a doctoral student of mine, Pete O'Connor. So the vertical axis is the share of total energy use in the United States that comes from different sources. And this includes traditional sources like human muscle power and draft animals and sailing ships and so on. And so you can see a couple of things. One, this big shift during the Industrial Revolution away from wood, which is that big blue blob at the beginning. Right? We mowed down literally every tree east of the Mississippi River. To first coal, and then oil, and then natural gas. And then more recently, slightly to nuclear power. And I don't have my clicker, but way down here in the corner, three colors up, that's wind. Solar, you can't put solar up because the width of the line will overstate its importance. So the point of this is how long it takes. So look at coal, which is that red area. So when coal went from, how long did it take for coal to go from 10 or 15% to half the energy budget? It's like 30 or 40 years. 30 or 40 years for a new major energy source to come on and make a significant penetration into energy. Natural gas took even longer. So now you want to run this out, and you want to tell me if you want, the renewable folks who want to do this with climate change, all right, solar and wind, yikes. This is what I mean about something that has to be radical. Something radical has to happen to fundamentally alter this and to generate a transition that wouldn't happen as business as usual. Here's another, I generated this graph a few weeks ago for my class, and I was really struck by it. Talk about inertia and the length of transitions. So this graph shows the types of fuels the U.S. uses to generate electricity. Okay? So the vertical axis is the total amount of electricity generated in the US over this period of time by these different sources. In 1980, fossil fuel, conventional thermal is fossil fuels, largely, natural gas and coal. 1980, 70%. 2011, 69%. So climate change, environmental crises, wars, how many wars over oil have we had? 2, 10, 12, whatever it is. Amazing. Very little change. Another major problem is that the market sends very perverse signals about energy. And it has, in particular, externalities, the environmental and human health externalities associated with fossil fuels. So an externality is the cost a good or service has on society that isn't borne by the users of that product. So it isn't reflected in the price. And the externalities associated with fossil fuels are staggering large. Rob Mendelson and Bill Nordhaus at Yale did a study a few years ago where they tried to calculate the external cost of coal. So this is the cost of health impacts, the cost of acid rain, the cost of climate change, all the external costs which we don't pay the price of gas or coal. And for coal, they calculated that the external costs were larger than the market value of coal. Which means that if those prices were internalized, coal use would stop tomorrow. And so climate change is a massive externality that all carbon fuels have, which currently, so it makes these fuels look a lot cheaper than they actually are. And it makes renewables look more expensive. So market signals have to be altered if we want to change this. Another issue is the cost of renewables. You showed that graph on the level. It's called levelized cost of renewables, and renewables are more expensive. This isn't a free lunch, folks. The cost, this transition to this solar, renewable, green future is not going to be cost-free. We'll probably be poor, in my opinion, economically speaking. There are other ways, non-economically, which we might be better off. Depends on how you value, how you value income and what well-being actually means to you. But the cost of wind is 50% higher than the new combined cycle natural gas plants. Solar energy is twice as expensive right now. Those costs have come down, way down in the last 20 years, and will continue to plummet. But with gas and other fuels still relatively abundant, technological change is also happening for fossil fuels, right? Lowering their costs. So the cost of renewables is still a significant barrier to their adoption. This is a huge one, right? So we have the most powerful corporate entities on the planet who have a vested interest in selling carbon. And they will lie, cheat, steal, cajole, and do everything else to try and tell you that climate change isn't happening. And if you don't believe that, go look at the Heartland Institute and the George C. Marshall Institute and all these other places that put out this climate skeptic work, and the scientists that do that, and look where their money comes from. It comes from them. And they've deliberately, these companies have funded, in various ways, a deliberate campaign of misinformation and lying, looking you in the eye and lying about the science of climate change. And so, yeah, we got to get on that. And the media has been culpable in this until very recently. Then, and I'll end with this, which is, in the United States, now I'm talking largely about the United States, the third rail of U.S. energy policy. So what's the third rail of U.S. energy policy? It's the demand side, right? What have I talked about this whole time? More pipelines, solar photovoltaic arrays, oil pipelines, right? Which is all on the supply side. Well, there's also this other part of it, which is how we actually use energy. Oh, yeah. And every president since Richard Nixon has made energy independence and energy policy a central part of their plan. They've all wanted to become energy independent. It doesn't matter whether you're Republican or Democrat, but nobody since Jimmy Carter tried it has had the courage, wisdom, ability, whatever you want to see, to engage the American public in a conversation about how we use energy. It's always, it's just this huge smorgasbord of throwing bones to every special interest group in terms of our energy policy. We'll build more of this, we'll build more of that. Well, what about the way in which we use energy? It's us, right? We're the ones that use energy. And Carter tried it in 1979. Those of you who are my age will remember this, where he sat in the Roosevelt Room in front of a fire in a sweater and talked in front of a national TV audience about how we had to use energy, and he said the word sacrifice, sacrifice, sacrifice. It decapitated him politically, decapitated him. And so we don't really want to talk about that. Is it okay to live 40 miles from work and get in a car alone and drive to work every day? You know, you could make an argument that's one of the most, we will look back on that and view that as one of the most absurd, self-centered, self-indulgent lifestyles that we haven't seen since the Roman times. So, but that's a conversation that we have to have, because how we use energy and issues related to how efficient we will use energy have to be part and parcel of discussions of energy, along with how we actually supply that energy. And with that diatribe, I'll stop.